What we're trying to do in this lab is to find the value of an unknown capacitor. There's various ways this can be done, of course. We could use time constants if we had a known resistor, or if we had a known inductor, we could then rearrange the resonance equation and then we could find C. So it just so happens I have a known inductor which is 250 microhenries. It's something that I've wound in class once before and measured with an LCR bridge. And today I've got unknown capacitor panel. And what I've done, I've had a sneak preview in the end of this panel, and I've seen that some capacitors are quite physically large and some are quite physically small. So common sense should suggest that the small capacitors are going to work with higher frequencies. So high frequency, microhenry style inductor, small value capacitor. I think we should be able to find the resonant frequency quite easily with this circuit. And then we need to explore this a little bit more. Unknown capacitor. We need a signal generator that's going to be able to sweep the approximate frequency that we're after. Now I'm suggesting this is going to be maybe between 100 kilohertz and 1 megahertz. That's just at a guess. That'll be the first frequency that I'll sweep. I've put a 100 ohm series resistor, and then I've put the series inductor with the unknown capacitor, the oscilloscope probe across the series combination, and then when we do reach the resonant frequency, of course, the vectorial addition of these, they'll cancel and there'll be a short circuit across the two components. So the voltage at this point here will drop very, very low, close to 0 volts. And then I can look at the frequency and I can go to the equation which I've already transposed. We started with the frequency of resonance was 1 on 2 pi root LC. I've changed this around to put just 1 on the right hand side, and then I've worked my way progressively down through it till finally I get rid of this square root and square the right hand side of the equation. And then lastly, if I want C, it'll be this divided by L. If I want L, it would be that divided by C. So this would also work out if I had a known capacitor but an unknown inductor value, and I wanted to find the value of that inductor. Quite a handy thing to be able to do in electronics using an oscilloscope and a signal generator, frequency counter, and a bit of common knowledge. So we'll work our way through this then. I've wired up the circuit. I'm sitting on about 6.7 kilohertz at the moment. Got the oscilloscope with the waveform across the inductor and the capacitor, and I'll just sweep up through the range there. Already at 56 kilohertz, I'm going up in decades here. I've reduced that waveform quite significantly. Ooh, we hit a bottom, and then on the other side, 156 kilohertz, I come up again in voltage. So it seemed to dip at around about 96 kilohertz, but that's going 96 to 106 down to 86. To be a little bit more accurate there, I need to change the function generator so that I'm only sweeping with kilohertz intervals now. Oh yes, I've got a lot better resolution. I seem to be around about 104.7. I'm going to call that 105 kilohertz. And what we need to do then, I've left my equation sheet on the front desk. We need to take that 105 kilohertz, plug that into our equation, and that will give me C. And look, like I say, I've left my other sheet of paper at the other side of the room, but when I ran the figures on it, I got about 9 nanofarads. Is that my other sheet of paper there? Oh, thanks, Brandon. That's just what I wanted. I've got some scribbles that I've done here, preliminary scribbles. I got 9.2 nanofarads. And then, look, we can take the lazy way out after we've done all of that nice maths and playing with fancy equipment. I can get the DMM and I can use the capacitor test function, unknown capacitor. I did use that with the first capacitor there, and it measured 11 nanofarads. So 9.2 nanofarads with the oscilloscope and signal generator, and my known inductor. In fact, the known inductor was probably closer to 240 microhenries. It was 242 microhenries measured on my Escort LCR meter. Don't know how accurate this is, but if I plug that value in, I may even be closer to the 11 nanofarads that we got here. I mean, let's face it, everything has tolerances, and the Digitech DMM is going to have a plus and minus tolerance for the value of the unknown capacitor. The LCR bridge, a little bit of tolerance. Maybe the only thing that hasn't got so much tolerance associated with it is the actual circuit with the voltage and with the signal generator. So I'd probably tend to believe it's around about 9.5 or maybe even 10 nanofarads. 10 nanofarads would work out well. That'd be a 0.01 microfarad capacitor. This is the end of part 1. In part 2 of this, we'll have a look at using time constants to find the value of an unknown capacitor. This is Greg Moore for New South Wales TAFE.